Okay, picture this. You're in a big technical interview. They lean in and ask you to explain the real core of Retrieval-Augmented Generation, RAG. How do you totally nail that answer? Well, today, we're going to break down the magic behind it all. Embeddings. This is the tech that lets an AI understand meaning, not just hunt for keywords. All right, let's get you prepped. Here's the roadmap for today. We're going to cover 5 key questions. First up, what are embeddings anyway? Then we'll talk about picking the right model, your translator. We'll also tackle a super common mistake, the mismatch problem. After that, we'll walk through how you actually build one of these systems, and finally, we'll look at how a computer literally measures meaning. By the end of this, you're going to feel rock solid on this topic.
So let's start at the very beginning. A computer only understands numbers, right? So how on earth can it make sense of human language? That brings us to our first fundamental question.
So why do we even do this? What is the whole point of embedding text? I mean, why can't a computer just, read? What's the angle here?
The answer is this really cool process called embedding. You take any piece of text, a word, a sentence, whatever, and you translate it into a long list of numbers. We call that list a vector. But here's the absolute magic of it. That list of numbers isn't random. It's a mathematical fingerprint of the text's meaning. Okay, look at these 2 sentences. One says, refunds are allowed within 30 days. The other says, you can return products within 30 days. Now, you and I know they mean the exact same thing, but the words themselves are totally different. An embedding model is smart enough to turn both of these sentences into number vectors that are mathematically super close to each other. That's how the machine gets it.
And that right there, that's the whole game. We are moving beyond old-school keyword search where you had to guess the exact right term to find something. This is all about meaning-based or semantic search. It lets a system find stuff that's relevant to your idea, even if the words don't match perfectly. That's the real power of RAG.
So we know we need to translate our words into these special number vectors. But what's actually doing the translating? Well, that would be the embedding model. And you can think of it as your own personal translator.
So, how much does it really matter which model you choose? Does picking one over another really make that big of a difference to your system's performance? The answer is absolutely.
I love this analogy. Think of these models like translators. Some are kind of like a cheap travel phrase book. They'll get you the basics, but they'll miss all the nuance. But others? They're like a professional UN interpreter who gets all the subtlety and context. The quality of your translator here is absolutely crucial.
Let's look at a real-world example. Say a user searches for policy on damaged goods. A weaker model might get stuck on those exact keywords. It would probably completely miss a document that's titled Rules for Defective Products. But a strong model? It understands that damaged and defective are conceptually linked, and it nails the search every time.
So it all boils down to this really simple chain reaction. A better embedding model gives you better retrieval. Better retrieval gives the AI better information to work with. And that directly leads to better, more accurate final answers. It's that simple. Your foundation determines everything.
Okay, this next part is super important. It's a gotcha that trips up a lot of people when they're building these systems for the first time. You've picked a great model, fantastic, but you've got to be consistent, which brings us to a really key question.
What happens if you use one model to process and store your entire library of documents, but then you use a totally different model to process the user's question when it comes in?
Well, the whole system just breaks. It's kind of like you've drawn this incredibly detailed map of a city and all your measurements are in kilometers. But then you hand someone a GPS that only understands miles. The numbers just don't mean the same thing anymore. The maps don't align, and you're going to get completely lost.
So the best practice here is basically the only practice. It's non-negotiable. You have to use the exact same embedding model for both jobs, for indexing all your documents and for embedding every single user query. You've got to make sure everyone is speaking the same mathematical language.
All right, enough theory. Let's get practical. How do you actually put all these pieces together and build a real retrieval system? What does that pipeline look like?
So let's say you're building your RAG application. What are the essential parts, the key components you need to actually build it and then query that vector store?
It's really a 5-step process. Step 1, you've got your documents. This is your knowledge base, PDFs, web pages, whatever. Step 2, you use a text splitter to break them into smaller, more manageable chunks. This is really important for accuracy. Step 3, your embedding model turns each of those chunks into a vector. Step 4, you take all those vectors and stick them in a special database called a vector store. And finally, step 5, when a user asks a question, the system does a similarity search to find the chunks that are the closest match.
Now, I've said words like similarity search and closest match a few times, but how does a computer actually calculate that? What's the math? This brings us to our final and maybe most interesting question. So what is this thing called cosine similarity? And why is it pretty much the industry standard for this kind of work?
Cosine similarity is just a way to measure how similar two vectors are. The best way to think about it is to imagine each vector as an arrow pointing in a certain direction in this huge multi-dimensional space. Now, cosine similarity doesn't care how long the arrows are, which means it doesn't care how long your text is. All it cares about is the angle between them. If the arrows are pointing in basically the same direction, the angle is tiny and the similarity score is really high.
And what you get at the end is a simple score, somewhere between 0 and 1. A high score, like a 0.92, means the two pieces of text are incredibly similar in meaning. They're a great match. A low score, like 0.12, means they're pretty much unrelated. And that's exactly how the system ranks all the possible results to give the user the best one.
So there you have it. We've gone all the way from words to numbers and from numbers to actual measurable meaning. This isn't just theory. This is the engine that's making AI so much more context-aware and useful. So now that you really get how RAG finds information, the real question is, what are you going to build with it?